So welcome to the aromatic extension material. We're going to hit an awful lot of cool chemistry concepts over these movies. Some of them will stick, some of them the first time round will sort of sail by, but hopefully as we extend the discussion, as we do examples, those concepts will come back to stick. The first three movies are really just setting the stage, although at least in this first one I'm using an actual aromatic example. And the first big word here is resonance. We touched on resonance before in the extension movie for the molecular structures 1. Resonance is just a way in which we enhance a model that we might have of the structure of a compound or of an ion, in which we can explain something unexpectedly. We actually use resonance with our benzene. We have our two structures that we can draw of it with the localized double bonds alternating in a different pattern, and what we think is that the actual structure itself of benzene is that average of those two, what would be called resonance structures. In the same way, something like carbonate, when you draw the Lewis structure of carbonate, you have a carbon oxygen double bond and two carbon oxygen single bonds, but the actual structure of carbonate is such that all of the carbon oxygen bonds are the same length. So what we do is we say, well, there are three resonance structures for carbonate. In each one, the double bond goes to a different oxygen, and reality is the average of those three resonance structures. We're not claiming that carbonate at any point has got one of those structures and then it switches to another and then switches to another. What we're doing is we're modeling it so that the average of our models explains reality. Now, another way in which one can use resonance, and this is what we're going to be doing here, is to think of resonance applied to intermediates, reactive intermediates in a reaction, in which we can point out that the more resonance structures that a particular intermediate has, the more stable that intermediate is. And that's a theme that we're going to hit several times during this little discussion. Let's actually apply it when we're thinking about what we've already talked about in aromatics. There is our intermediate for an attack of an electrophile E on benzene. And we said that when the electrophile comes in and we pick this particular hydrogen here, well, then electrons from this carbon-carbon double bond go to making a bond to the electrophile, leaving behind a carbon that is deficient in electron density. And then, of course, I said that in school you learned about this Wheeling intermediate, in which the positive charge is not localized on this one carbon, but it's spread around the entire carbon ring. And I promised that while you might not get to that at A level, we would get to it in the extension material. So here it is. Now, essentially, the way that we model delocalizing that positive charge is we generate three different possible resonance structures. Again, none of these resonance structures actually exists, but the reality is some kind of average of them. Okay, and the way that we model and move between one resonance structure and another is we think about moving our electrons, in particular our pi electrons, or in later ones you'll see lone pair electrons and so on. So here what I'm going to do is I'm going to say, well, here's one possible resonance structure in which we're modeling the positive charge localized on this carbon. Well, imagine if the pi electrons in this bond here weren't in this bond here, but instead they were moved using our cute little green curly arrows to being in that bond there. Now, what would that mean that we have? Well, what that would now mean is that we got a double bond here. So this carbon is no longer positive because now it's got the double bond to this carbon. This carbon hasn't changed at all. It's still single and double bonded to two other carbons, but this carbon down the bottom here has now lost its electrons. So now by creating a new resonance structure, by considering the movement of electrons from one localized double bond to another localized double bond, now we can say, well, we can think about the positive charge not just being on carbon 2, if you like, but carbon 4 as well. Now, these are not real structures. This is not a real reaction. So we use this little double-headed arrow to indicate the relationship between two possible resonance structures. Now, there's a third resonance structure we can draw. Can you come up with what it might be? Well, I'll tell you. What we can now do is we can say, well, let's think about these pi electrons here in this double bond, instead of being between, say, carbon 5 and carbon 6, using my original counting, maybe between carbon 5 and carbon 4. So we'll take those 2 pi electrons and move them to that bond. Now we get this picture. So now by moving those electrons, we haven't affected this carbon here, call it carbon 5, but we have very much now taken care of the positive on carbon 4. But by moving electrons from this bond to this bond, from this pi bond to this pi bond, now this carbon 6 has got a positive charge. Now all 3 of those resonance structures combine to give us the overall average that we claim as the Wieland intermediate. So we can come up easily with 3 possible resonance structures to describe the intermediate that's formed during the electrophilic attack of E, our electrophile, on benzene. Now generally, when you have an intermediate, the more resonance structures you can draw for it, the more stable the intermediate, and of course the more stable the intermediate, the more likely the reaction is that leads to that intermediate. And that's one of the really, really important concepts that we need to keep about us as we go through this material. So as we go through our discussions associated with substituted aromatic compounds and their reactivity, what we're effectively talking about is having a benzene ring, and we're world experts on what benzene does, that has a group attached to it, a substituent attached to it. And what we want to know is what effect is that substituent going to have upon the reactivity of the benzene? Is it going to affect it at all? Well, you're just going to think really about electronic effects in this particular extension topic. Steric effects, the effect of big bulky groups, is important, but it's not something I want to really get into at the level that we're discussing things. So we're going to be thinking about electronic effects from these substituent groups, and we're going to break them down into how do these substituent groups affect P or pi electrons, and how do they affect sigma electrons. So we'll start off with just continuation of our thoughts on resonance. Okay, and the fancy word for resonance effects are mesomeric effects, and we'll see M for short. Now, if we have a group attached to a benzene ring, that group can have either 0 mesomeric effect, or it can donate P or pi electrons into the ring, or it can try to suck or accept P or pi electrons out of the ring. When it's a donation, we're saying that this mesomeric effect is giving electron density into the ring, and so that's a positive. And when it's accepting or trying to remove pi electron density for the ring, we say it's got a negative mesomeric effect. Now generally, positive mesomeric effects can stabilize a positive charge because they're sharing some of that electron density. And we saw the use of resonance to explain spreading that positive charge out around the ring in the previous slide. And of course, if positive mesomeric effects help to stabilize positives, well then accepting or negative mesomeric effects can help stabilize adjacent negative charges. So I'm just going to give a couple of examples just to emphasize our use on this. Consider this carbocation here. Okay, now of course carbocations we've seen before quite a bit. We know that the more substituted a carbocation is, the better. What we haven't talked about is how this carbocation here, a so-called alkenyl cation or allynyl cation, is really, really super stable, because we can use the pi electrons in that carbon-carbon double bond to help to stabilize that positive charge of the carbocation by providing another resonance structure. Take the 2 electrons, pi electrons, from the carbon-carbon double bond, push them over towards the carbocation, and we get this new resonance structure in which now we've stabilized that positive charge over 2 carbons rather than just 1 carbon. And it doesn't have to be just pi electrons. Indeed, most of what we're going to see in our discussion of this aromatic reactivity is not pi electrons, it's lone pairs, usually as p electrons. So again, think about this carbocation that is attached to an atom that has some lone pairs on it. Well, that atom with the lone pairs can use its electrons, it can donate its electrons, it can have a positive mesomeric effect to stabilize the charge like so, put 2 electrons into the bond. Now that carbon doesn't have a positive charge anymore. That positive charge is over on the atom that had lone pairs. Okay, so 2 ways in which we can think about a positive mesomeric effect stabilizing a positive charge using pi electrons or using p electrons from a lone pair. Now, we haven't talked much about negative carbon atoms, so-called carbanions, but we will touch on those in later modules. But negative carbon atoms, carbanions, can be stabled by having a mesomeric acceptor, right? A p or a pi electron acceptor. And so, for example, here, if you look at a very important species that we'll discuss later on, a negative carbon close to a carbon or adjacent to a carbon-oxygen double bond, well, then you can put the electrons from that negative charge into a bond to that carbon that is attached to the oxygen, because then the oxygen can accept some of those extra electron density there to give it this resonance structure. And then, of course, we could go backwards if we wanted to in that direction. So groups attached to a carbon atom, in the case that we're interested in here, groups attached to aromatic rings can have positive mesomeric effects. They can push p electrons or pi electrons into the ring, and groups like this are halogens, OH, OR, SR, that we won't touch on too much, amines that we'll talk about later on, NH2 and NR2 and so on, and of course we've seen the carbon-carbon double bond. All of these first examples have the lone pairs that we talked about, carbon-carbon double bond, also other benzene rings and so on, but I haven't wanted to specifically put that down, can do it via the pi electrons. And then should you have a group that is a negative mesomeric one, of course pulling electron density out, well, examples of this are groups that have the carbon-oxygen double bond like we see here. Nitrogen without a lone pair, okay, nitrogen that has a lone pair can use it over here like in the amines and so on. Nitrogen without a lone pair, as long as it's attached to some other electronegative atoms, it can be a negative mesomeric acceptor. Cyanide, and interestingly, carbon-carbon double bonds can do both. If they need to donate pi electrons, they can do so. If they need to accept pi electrons, they can do so. Anyway, we're going to talk about mesomeric effects for our substituents, positive ones that can put pi electrons into the ring when it's attached to the ring, negative mesomeric effects that will try and take pi electrons out of the ring.